Okay, so I'm assuming that there was a better technological way of doing this video, but here we are. So this is the last slide in the slide deck from yesterday. And so this is the best tip for problems involving potential due to charged objects. And it's to infinity and beyond, except it's not beyond. It's to infinity and back in, okay? So take a charged object. This could be, two concentric spheres. These could be conductors or insulators. So this actually works for any of those. But start at infinity, and then you want to go back to the object. So this is how it's going to go. You start here, out at infinity, because the glorious thing out there is that the potential is 0. It's defined that way. And so that will be very useful for us. So you start there, and then you go back in. And you say, okay, well, what's the potential at the surface, right? So we're at little r equals big R, where big R is, this radius right here. So the real question is, if we're thinking about the potential at the surface, I'd like to ask sort of, is there an electric field between the surface and infinity? Okay? Because if there is, then the V at the surface is going to be different than V at infinity, right? It's different than V equals 0. So just step back for a second. Electric fields and potentials. If there is an electric field, there must be a potential difference, okay? You can also think about it the other way. If there's a potential difference, there will be an electric field, okay? So the question is, if those are different, how can we calculate it? How can we calculate that potential? Well, you guys know that using Gauss's law, you can calculate the electric field in any region you need, right? Remember, there were a bunch of sort of different regions we could talk about here. We could talk about R greater than big R, maybe the R in between, whatever, I don't know. Maybe this was actually A and B, maybe that was A. But you remember all those Gauss's law problems where you had to calculate the electric field in any of the possible regions. You're going to use that electric field now to calculate the potential at different places using this equation, all right? So remember, this is just that relationship between potential and electric field. And again, you sort of want to think, I start at an initial point, I go to a final point, and I'm looking at the electric field in that region where, sort of in the initial and final. So the potential at the surface. So what did I say to do? You start at infinity. So there it is. That's the initial, and then we're finishing at V at big R. Okay, that's the potential at the surface. And there's initial, there's final. This electric field is whatever electric field exists out here. And again, you can figure that out using Gauss's law. What's really nice here, of course, is that the V at infinity is 0. Okay, so you can use this to figure out the potential at the surface. See, that's literally VR. Okay. And then once you get to the surface and you're asked for the potentials in these other regions, you just keep going. So you sort of build it that way. Because when you do initial, final, if you're trying to figure out the potential at this surface, then this will be your initial, this will be your initial, this will be your final, okay? And you just figured this out from starting out here, okay? So you get this, and you go there, and then you can do this to there. So it's a matter of using Gauss's law to get the electric fields, starting at infinity, and then going in. The other thing I wanted to mention while I have your attention is if we have 2 conductors and they are connected by a wire. So there was a question on your test where it talked about 2 identical conductors and they touched, and then you had to just assume that the charge will distribute evenly, right? But that was because they were identical. But we can actually have the discussion of what happens if I have 2 conductors, they have different charges and different radii. okay? And then I connect them with a wire, okay? So because they're conductors and because I've connected them with a wire, charge will flow until, take a moment and think about that. You know, why do charges flow? Charges will flow because there's an electric field exerting a force on them, right? What's going to cause an electric field? A difference in potential. So when will these stop flowing? When they have equal potentials, okay? So that means that VA equals VB. And if you're just looking at the surface, hopefully by this point you realize that the potential at the surface will just be like it is a point charge at the surface. QA divided by RA, right? KQ over R. And then this guy is going to be KQB over RB, right? So who's going to end up with more charge? Right, clearly RA is less than RB here, right? So hopefully you will see that to get the same potential, you'll have less charge end up on sphere A. Hopefully that makes sense to you, right? Because it's just sort of, you have a smaller surface area to spread that charge out over. So that's going to be QA is less than B. What about the electric fields at the surface? Think about that. Who has a bigger electric field? Okay, so this one's a little bit fun to think about. So the electric field at the surface of a sphere is going to be, right, just in general, K times its total charge divided by the radius, right? So we've done that a bunch of times. You can prove that again using Gauss's law. Okay, so in this case, so we've got KQA over RA squared. That's KQB over RB squared. All right, so which one of these is bigger? Well, what do we know? We know that KQA over RA is KQB over RB, right? Because that's how this was determined, right? Because we put this wire between them and the voltages were the same. So what is this? This is, right, VA divided by R, right? And that's VB, or sorry, divided by RA, and that's VB divided by RA. So because RA is less than RB, EA is greater than EB. So those are some fun things that you can sometimes do with conductors.